Hello students, welcome back. Let us resume our discussion in section 2. Previously, we reached up to the dense distribution of real numbers. What do you mean by that? Between any pair of distinct real numbers, there exists at least one real number. And that's not all. There exists one, so between z and y, there got to be another one. And between that and y, there got to be another one, and so on and so forth. Therefore, what conclusion can I draw? There exists at least one real number in between x and y. Consequently, there are infinitely many. Now, how do you prove the first real number exists so that infinitely many follow? We can simply take the average. Between x and y, we can find x plus y over 2. And we can algebraically prove that this is between x and y easily, like this. But most students will prefer the geometric expression here. Yes, we can do that because the set of all real numbers is linearly ordered. So we can arrange all real numbers along a line. Actually, not only that, the set of all real numbers fills up the line completely, but that's a different story. That's section 3 topic. For now, let's focus upon section 2 topic, just ordering property. Yeah, they are linearly ordered, so we can arrange them all. So this kind of graphic makes sense, not just for real numbers, but also for rational numbers and even integers. For rational numbers, we can take x plus y over 2. That's another rational number in between. But for integers, that doesn't always work. For example, x is 0, y is 1, then this is 1/2. That's not an integer, so we have discrete structure. So we do not have dense distribution for integers. For rationals, yes. For reals, yes, because we can find something here completely through the arithmetic expression, x plus y divided by 2. By the way, this is not the only way to get a real number in between or rational number in between. X plus y over 2 is midpoint here that divides this line segment 1 to 1. See that? 1 to 1. In general, however, we can devise like this, so that this number divides a line segment at the ratio of m to n. In this particular case, 2 to 3. Let's run this program again. 3 to 2 this time. Let's do it again. Ratio of 5 to 2, and so on and so forth. Even more so, m and n do not even have to be integers. In short, there are infinitely many different ways to get z, even initially. And once you get z, you can use the same property to get the next, and so on and so forth. Conclusion? There exists at least one real number. Consequently, there are infinitely many real numbers in between. So that's the dense distribution property of real numbers. From that, interestingly, we can prove this. The smallest positive real number does not exist. How can you prove this part B from part A? Think about that. Stop the playback and think about that. Did you get it? What do you want to prove? You want to prove that the smallest positive real number does not exist. In other words, the minimum does not exist. Yeah, there are various different expressions of that for all positive real numbers. Interval 0 to infinity or R plus. Yeah, all those means the same thing. The minimum of the set does not exist. Well, what if you assume it existed? Can you draw a contradiction from there? Try. Stop the playback and try. Did you get it? Suppose that your minimum is m And how do you utilize this to m? Alright, finally the answer is coming. You can find a real number between 0 and m like this, half of m, or 0 plus m over 2, the average. Yeah, we use the average here, like that. Anyway, we found another positive real number between 0 and m. Conclusion: this positive real number is less than the minimum. There goes the contradiction. The minimum cannot exist. The smallest positive real number does not exist. And that's coming from the dense distribution property. Alright, between any pair of real numbers, there exists at least one real number in between. From there, we can deduce that the smallest positive real number does not exist. Now, how do we apply this? The most important application I can think of are these, the epsilon principles. For any positive real number epsilon, x is less than epsilon, then x is less than or equal to 0. So what do you mean by this? X is a real number that is less than every positive real number. If x is a positive real number, then that's smaller than every positive real number, so it's the minimum, but the minimum does not exist. We already established that, right? So from A, the dense distribution of real numbers, the dense distribution, we got part B, the smallest positive real number does not exist, and then that leads to the first epsilon principle. A real number that is less than every positive real number epsilon has to be less than or equal to 0. Now, this can be generalized to this one. Here, in place of x, I can replace x minus y. If I do that, then I'm going to get this. So here, x minus y goes there. Here, x minus y goes there. And that's precisely what we have here. Flip y to the other side. So from here, some manipulation, a substitution, yields this. So part B can be considered as an immediate corollary of part A. And then part A came from this part B of 2.4, and that came from part A, the dense distribution of real numbers. By the way, the rational numbers have the same property here. Therefore, this epsilon principle works for rational numbers as well. Now, can you apply the properties of absolute values to prove part C and part D from part A and part B? Stop the playback and try. Can you get it? Well, let's see. What do we have here? This we know. And then in place of x, we put absolute value of x, and therefore absolute value is less than 0. That's the conclusion we get. And then after that, what can you do? Absolute value is less than or equal to 0, but it cannot be strictly less than 0, so it has to be equal to 0. Oops. Therefore, x is equal to 0, and is not what we have over here. Okay, and then using the same argument as before, you can extend this to the general case. I'll leave that to you. So what do we have? all these, the epsilon principle, come from this. The smallest positive real number does not exist. And in turn, this comes from this. The set of real numbers are, the set of all real numbers is densely distributed. The real numbers are densely distributed along a line. Okay, alright, that's a good statement. Sorry, I don't know what just happened. What's happening here? Okay, alright. I got it back. Maybe I had some unstable connection or something. Okay, epsilon principle, and don't panic. The application of epsilon principle can be really rough, and if you're ready to real analysis, then you'll remember. But as far as getting up to epsilon principle, it's not too bad. Basically, everything comes from this dense distribution of real numbers. One more thing, this property applies for rational numbers as well, right? Therefore, all the epsilon principle, all here, they apply for rational numbers too. I mean, we usually utilize this to real analysis, but you don't really have to do this in real numbers only. You can do those for rational numbers too. Can you do that for integers? No, you can't, because integers are not densely distributed. Therefore, all these do not follow. Okay, how much time do we have? Epsilon principle. Okay, let's go to the next application. Triangle inequality, and that's pretty simple. Yeah, here we go. Absolute value of x plus y is less than or equal to the absolute value of x plus absolute value of y. Here in the right hand side we have positive plus positive, but in the left hand side we may have some cancellation. And the proof is really tedious. It's easy but tedious. Here's a sketch. When x and y are both positive, then we have equality. Absolute values just disappear. When x and y are both negative, then instead of absolute value we get negative of this, and negative of that. Consequently, the equality holds. Again, x is equal to 0 or y equal to 0, we have equality. Now, finally, when x and y have opposite sign, x times y is negative. In other words, x is positive and y is negative, and vice versa. X is negative and y is positive. In this case, we're going to get strict inequality there. Well, the details are left to the students. It's just tedious. It's not difficult, just tedious. Let's consider some variations of those. Let's see. Here, in place of just x plus y, we can consider x, y, z to get this. And then here's another variation. Flip subtraction to the other side, then you're going to get addition. And then finally, applying this inductively to any sum so that absolute value of sum is less than or equal to sum of the absolute values. They all come from here. Proof of this, well, okay, I'll show you. It's not too bad. X is like this, and I'll apply the triangle inequality and flip this y to the other side. It's easy. How about this? Just a bit of manipulation. X minus y, y plus z, and then apply the triangle inequality of previous. Again, it's easy. And then finally, this one is mathematical induction. Base case 2, we have it. In general, apply the induction. The details are left to the students. Okay, that completes section 2.